potential energy. So if you remember, we had learned that if you have a point charge at any place, a positive point charge, suppose small q over here. So we have learned in the first chapter that it will create electric field, which is radially outward around it. Okay, and the last chapter we have learned, like last section we have learned that this point charge will create a potential around it, and you can have equipotential surfaces. Okay, spherical surfaces, equipotential surfaces you can have. Okay, since this point charge has spherical symmetry, because its electric field are actually radially outward from a point charge, so it has a spherical symmetry. So even though my spheres are not perfect, so you will have concentric spheres, actually spherical surfaces as equipotential surfaces. Now look, if you have a point charge over here, okay, then it is creating a field as well as a potential over the region. And now if you bring another charge, suppose I take this as q1 and this is q2 in this region, okay, in the region where the field or potential created by q1, if you bring this, okay, to somewhere here, which is actually r distance away, so the potential energy which is denoted by u will be given by q2, this is q2 into v of the potential created by the charge 1. So this is the potential energy. Okay, so this is what we are going to learn today. So what is the potential at r distance away from the like created by q1 charge? So that will be q1 by 4 pi epsilon naught r. So potential for a point charge vary with distance as 1 by r. Okay, that means inversely proportional to the distance you go from the charge. Okay, so now if we just put this value, so you will get q1 q2 by 4 pi epsilon naught r. This is called potential energy. Okay, so the charge into the potential created by the other charge. Now look, this we have learned for a single charge or maybe for a two charge system. If I have, okay, many charges, okay, like this, so this kind of concept you might have learned again like before in the 11th standard from gravitation. Okay, gravitational potential energy and all you have learned. Actually, whenever we talk about potential energy, so potential energy term actually is valid for conservative force. So gravitational force as well as electric force both are actually conservative in nature. Okay, conservative in nature. What does it mean? It means that when you work against electric field or gravitational field, that work done will be stored as a potential energy. That work done will be stored as a potential energy. Suppose so I have, suppose a system of charges like q1, q2, q3, and this is q4. I have 4 charges and I had created a system of 4 charges. So this is a system of 4 charges. So you have been asked to calculate. The problem is like this, that I have system of 4 charges and charges are given, and suppose from arbitrary origin their distances are r1, this is r2, okay, this is r3, and this is r4 from some arbitrary origin. This is origin. Okay, this is r2. So system of 4 charges. So The question is to create such system, how much potential energy or how much work you have to do. So what is the question is, what is the potential energy held by this system of four charges? Okay, or in other words, I can say, if I want to create such a system of four charges, Q1, Q2, Q3, Q4, then how much amount of work I have to do. So what is the definition of potential energy that we have learned already? In this case, what you have to do, you have to, whenever I talk about potential energy, you have to have some reference point. Okay, Nikhil, can you tell me what is the reference we have taken? Reference means when the potential energy is zero. The place where the potential is zero, that is the reference. Suppose a gravitational force, gravitational potential energy at the ground, it is zero. So this is reference. Okay, this is called reference because the gravitational potential energy is zero at the ground and certain height. With respect to this ground, some potential energy is there, that is mgh. Similarly, if this is the height h, okay, so how do we define potential energy? The amount of work we have done against the gravitational force. Suppose the object has mass m, so I am just lifting the m mass, so what will be mg? So the gravitational force is downward, I am just lifting it up to h height, so I am doing certain work against the gravitational pull. Excuse me. So this is the work I have done. Force into displacement. That is the mg is the force and displacement is h. This is the work I have done on the object to bring up to this level. Okay, from where? From the reference level. So in case of electrostatic force, what is the reference level you take? I take the reference level as the infinity distance because my potential, if I write an expression for potential, you look, potential for a q charge will be q by 4 pi epsilon naught r. So this is a potential as a function of r. If I set r as infinity, what will be this potential? Potential, this will be zero. Right? If the potential is zero, so potential energy also will be zero at infinity. So what I have to do actually in the beginning itself, I should not take that I have system of charges like this. What I have to think? I have to think that I have a region of space over here where I am making the system of four charges. But initially it is empty. Okay, empty space. Initially no charge is there. Okay, no charge is there. So what I have to do? I have to take charges from infinity to this region of space one by one. Suppose I bring one charge. Suppose I bring q1 charge from infinity to such point. This is q1. Okay, here. Okay, this is suppose from arbitrary origin. This distance is r1. Okay. So at this position, I have brought from where? I have brought from infinity. So initially, was there any electric field in this empty region? If there is no charge, then field as well as potential will be zero. So if there is no electrostatic field, okay, or potential, I like against whom I will be working? I have nothing to work against any force field, right? So initially, since this region was empty, there was no force, so I did not have to work. Okay, I did not have to work. So work done to bring the charge 1 is 0 now. Okay, work done is 0. Now see, I'll be bringing my second charge from infinity. Suppose this is infinity. Okay, according to our discussion now. See, I'll be bringing the other charge to Q2 at this position. Okay, so which is actually from arbitrary origin at R2 distance away. Okay, so when I bring this Q2 charge, can you tell me what will be the work done? So work done will be, see, I have to see whether there was electric field at all or not. See, already my Q1 charge is actually sitting over here, right? It is sitting over here. So it must be creating certain field or potential. So what is that potential? So suppose that potential at this distance, suppose this distance is R12. Okay, potential created as at this point due to Q1 is how much it is? Q1 by 4 pi epsilon naught R12. This is the potential created by Q1 over here. So when I bring the Q2 charge, I have to actually do certain work, because I am actually doing work against the electric field, repulsive force actually. You look here, this is a positive charge, this is also positive charge. So this will repel actually. So I have to do work against the repulsion. So I have to do work actually in this case. So what is the work done? This will be Q1, this is the potential created by the charge Q1 into the magnitude of the charge Q2. So I got the potential energy. So if I have simply a two charge system Q1 and Q2, what is the potential energy? Then I have to write Q1 Q2 by 4 pi epsilon naught R12. Okay. Okay, if this is a system of two charges, now I am telling that I have for another two charges to bring. So another charge, third one, I will bring suppose here, somewhere here. Okay, this is Q3. I am bringing from infinity again. So look, already two charges are sitting over here. So they will create a potential, okay, at R23 distance, this Q2, and Q1 also will create a potential over here. So I have to actually work, see, the work done I can write, if I write W3, see Q, anyway W1 is 0, I am just removing this part. So W2, W3 will be actually Q3 into potential created by 1 and potential created by 2. Okay, where at this position. So how can I write that? Q3, and see this will be Q1 by 4 pi epsilon naught R13 plus Q2 by 4 pi epsilon naught R23. Okay, this is the work done to bring this Q3 charge. Okay, similarly, I think that the last one you people should tell me. So Q4 I am bringing somewhere here, Q4, and see it is actually at arbitrary origin, R4 distance away. So can anyone tell me what is the work done here? So Q4 into potential created by 1, potential created by 2 plus potential created by 3. Okay, all these three will be actually because see the fourth charge, when I am bringing the fourth charge, I am already seeing that Q1, Q2, Q3 they are sitting over there. They will be creating a potential around this point. Okay, where I am bringing the fourth charge. So look here, I have to write Q4, then Q1 by 4 pi epsilon naught R14 plus Q2 by 4 pi epsilon naught R24, and this will be Q3 by 4 pi epsilon naught. This is 34. Okay. So this is W. So what will be the total energy, potential energy? So the W1 plus W2 plus W3 plus W3, W4. So whatever total work you have to do to bring all the charge individually, okay, you have to add all of them, then you get the total potential energy. Okay. Okay, so this is how you have to calculate the potential energy for a system of charge. If you have any doubt, you can ask me right now. Nikhil, do you have any doubt? Or Priyadarshini, do you have any doubt?
No, sir.
Okay, okay, I'll show you in your book. See, the same thing has been told over here, but you might be having a question, right? You might be having a question, sir. You have brought the charges one by one, like Q1 first, Q2 then second, and then Q3 like that. Okay, but what if I bring the fourth charge first, and then I bring the like opposite sequence, right? Fourth one, then third one, then second one, and then first one. So what will be the potential energy? Whether there will be any changes? Can anyone tell me? Nikhil, can you tell me whether there will be some other value of the potential energy or the same value? Okay, Priyadarshini, can you tell me? Will there be
Sir,
any change in the value of the potential energy? If I take any other sequence to bring the charges?
no, sir.
No, no, it is correct. Yeah, you are right. Actually, it is no. There will be no change. Okay, because see, so you might be asking why it is. You can do it mathematical. You can just do and see, but otherwise also, since it is actually see, this is a conservative force field. So work done does not depend on path for a conservative force field. For a conservative force, work done does not depend on path. If I have, suppose I have a path, I have to go from A to B. This is A point. I have to go to B. Okay. If I go directly, suppose work done is 0 or W0. If I go in this path, suppose this is W1, this is this way, this is W2, and some other way like this, W3 like that. Whatever it is, the work done is going to be same, because the work done does not depend on the path. It depends on the end points where you are going. It depends on the end points. Okay, so ultimately you are going to the end point B. Okay, because again, like work done is actually, yeah, so this is the thing. Okay, so this is because of the conservative force, for which the work done does not depend on the path you follow, but it depends on the final position. Okay, so that's why you, if you bring third one first, then first one, then second one, then fourth one, anyway you take, the potential energy is going to be the same. Okay, now see here, for three charges it is written. You can just look your book at, okay, so you just read and then you can understand again. And one more thing I just wanted to say, so for our convention, we have taken, it is actually all the charges are positive, but if if I would have taken positive negative mixture, then also see potential energy will be either positive or negative. That depends on the charge. So in this case, I am saying, see, in this case, when I have taken all the charges as positive, I am saying that I am bringing the charge. Suppose this is a point. I am bringing the charge from infinity to this point. Okay, but, and that is actually against the electric field. Against the electric field. Electric field is in this way. I am bringing against the electric field. Okay, or repulsive force, because this charge is also like there is a positive force field over here. But if you have negative, if you are negative charge, you are just constituting a system of positive and negative mixture, q minus q and then 2q like that, whatever. So when for minus charge, what you have to say, so minus charge means if suppose there is a positive charge and there is a negative charge. Okay, so obviously there will be an attraction. So you have to actually do what to keep this charge at its own position. Okay, because attraction will pull it. To keep this charge as it is here, you have to do certain work. or in other words, I can say that I have to take the charge from its position to infinity. Okay, because there is attraction this way, you are the attractive force, and you are taking the charge from there to infinity against the attractive force. Okay, against the attractive force. So we have to think in that way. Okay, but the potential, so in this case actually potential will be negative. Okay, potential will be negative. The other case, it is potential is positive. Okay, so this is the thing. There is a nice example in your book. Okay, there is a nice example in your book. We'll just I'll just give you the summary of this problem. See, there is actually positive, negative, all type of charges are there. There are four charges initially. See, yeah, like at A, so this is actually a square. Like at each vertices, you have brought like some charges like Q, minus Q, and all. So you have been asked to calculate, find the what required to put together this arrangement. That means to make this kind of arrangement, how much amount of work done you have to do. So you have to, what you have to do, see, they have, see, I think d distance is already given, d. So what you can do, you just initially think that this square, on this square there is no charge. So now you bring one by one, charge one by one. First you bring the positive q charge at O, at A point, okay, at the vertices A. So initially when there was no charge around it, okay, so there will be work done 0. Now if you bring the other charge at B, that is minus obviously here, so potential already created by this will be here, or the field created by positive charge at A will be actually affecting this charge. That means you have to do certain work. Okay, here positive force field, but here it is negative charge. So you have to do certain work to separate the the charge from here to infinity. Like that you have to think. But anyway, this will be like minus q into the potential created by this guy over here. So q by 4 pi epsilon naught d. Okay, this is the d distance into small q. So minus q square by 4 pi epsilon naught d here. Okay, first work done. Like second work done due to bring this minus q charge over here. Similarly, if you bring the other charge at C, so you have to see there are two force field, like two charges already here. They will be creating a field around it. Okay, one will be positive field or repulsive force. One field will give you repulsive force. Another force like field will give you attractive force. So for both of them with the proper sign, you have to calculate the work done. Okay, then you bring the fourth one, and that time you have to consider the potential created by all three charges over here. Okay, and multiply this minus q with like v1 plus v2 plus v3 like that. Okay, as I was doing. So if you, as you do it properly and add all of them, you will just get the total work done. It is like here, it is given like this. Okay, it is given like this. So you can just calculate it. Okay, I'm not calculating because we have to finish little more. Okay, so we'll go ahead with the theory part. You just see this problem already solved. If you suppose you can't understand somewhere, you can ask me in the next class. Okay. Now we'll see the potential energy of a single charge when the charge is actually in an external field. So far, okay, so I'll just tell you the situation. The situation is actually, suppose you have a charge, positive charge or negative charge, anything, a single charge. Now see, earlier what I was telling, that there is a force field created by another charge over here, okay, another charge, and you are bringing this charge into this field, okay, inside this the field created by capital Q over here. But in this case, we don't know what is the origin of the potential or field. It is something called external source of field. Okay. Okay, external source of field. Okay, and nothing to do with us. Okay, nothing to do. We don't have to consider like how the construction of the source of the field created. Suppose, see here, what is the problem? Problem is like this. So I have a region. Okay, suppose x is equal to 0 and this is x is equal to d along the x direction. Okay, I have a region. So in this region, there is a constant. Sorry, not constant. There is a potential, varying potential. Obviously, the potential will vary with distance. So suppose there is a potential uh, in this region. Okay, there is a potential created by some external source. We don't need to know that what is that source is. Now, if I have a charge, some charge q, or I think I'll just take as positive e charge. Okay, positive, the magnitude of charge of the electron. Okay, magnitude of charge of electron is positive e. Okay, magnitude of electronic charge. Okay, so suppose I take take this charge and allow it to accelerate. Sorry, allow it to actually go through this. Allow it to go through this, actually this region. Go through this region. So what will happen? You know, like see, potential maybe here it is 0. Then potential will increase. Okay, some V1 which is greater than the previous. Then at this region maybe V2. Okay, again at this region maybe V3. So potential is increasing. Okay, look here, what will happen? The charge will be accelerated through this. When it goes through this, it will be accelerated. Actually, it will gain certain kinetic energy. And you look, obviously, see, if I have a potential, I can calculate the potential energy as well, right? So I just calculate the potential energy. Or at each position there is certain potential. So I can write the potential energy. So I was telling previously that Q into V, right? So in this case also, what will be the potential energy? E into V. This will be the potential energy of the electron when it is actually going through or accelerating or passing through this region of space where I have certain potential. Okay, but if this potential is actually not a fixed potential, this potential is increasing, suppose in this way along x direction. So it is getting accelerated from x is equal to 0 to x is equal to d. Okay, so what is the potential energy it has potential ev, and v, obviously v is not a constant, so v I can write vr. Okay, it depends on distance, like at whatever distance you go, it actually varies. Potential varies with distance or region of space. So the so now we have learned that when you have an electron or electronic charge, okay, electron, suppose electron, it is actually passing through a region of space, okay, a region of space where you have certain potential V, suppose at any instant of time, at any point in this region, it experiences a potential V. Then what will be the potential energy? Potential energy, it will gain actually E into V. This is how we'll express. So I have this as actually, this has charge 1.6 into 10 to the power minus 19 coulomb. Okay, and this is V. So we will say this is electron volt. Actually, this has, see, the potential. This EV has actually unit electron volt. Electron volt. This unit will be electron volt, not joule and all. Okay, this is not joule or volt per meter or something. Voltmeter. This is not the case. Here it is electron volt. Okay, that's why in short, if I have four, suppose 4 electronic charges, then 4 electron volt. If I have suppose 40 electronic charges, so I will write 44 electron volt. Okay, 44 electron volt. So this is the fundamental unit. Okay, this is another fundamental unit of energy. Okay, this is fundamental unit of energy. This is electron volt denoted by small e multiplied with capital V, and this unit will be using in atomic physics. Okay, atomic molecular spectra. Okay, atomic or molecular spectra. Or see, this is simply electron volt or milli electron volt. Okay, milli electron volt. But I have bigger units also, like giga electron volt, that means 10 to the power 12. Okay, multiplied electron volt into multiplied 10 to the power 12. Okay, then mega electron volt, these are actually bigger unit. So giga electron volt will be actually electron volt into 10 to the power 12. So that will be giga electron volt. Okay, EV into that. And mega will be 10 to the power 6 multiplied with 10 to the power 6. So, so these big units, these are actually of you, like this energy is a high energy. Okay, these are actually high energy. Giga electron volt or mega electron volt, these are high energy. So these units, mega electron volt or giga electron volt, this will be using in high energy physics, that is nuclear particle physics. Okay, nuclear physics or particle physics, or any radiation related nuclear radiation or any radiation related uh, problem will be using this very large unit. So, so you can now, so I think this is clear now, that if you have a positive or negative, whatever it is, if you have an electronic charge or any charge passing through a region of space where you have certain potential created by external source, and see, in this case, one thing you remember, since I have a single charge, I am not thinking that this charge also, when comes here, creates another electric field around it, and whether the potential created by the external source and potential created by this electron itself, you have to consider. It is not you don't have to consider the potential created by self or the field created by self. Okay, if you have, suppose, another charge, okay, if you have another charge, suppose two charges are there at the same time, suppose one charge is actually 2e, another charge is e, at the same time they are just crossing this region where I have potential V, certain potential V. So suppose this is E and there is 2E here. So in this case, you have to consider the potential created by this charge as well. Okay. If I know the distance between these two, so you have to actually consider. So the potential, actually you have to now, if I ask you what is the potential energy, okay, potential energy of this electron, then what you have to write? The potential energy means, see here, obviously E capital V, the potential due to this external source will be there obviously, and see into this also will be there, 4 pi epsilon naught, and the distance between them are. So this also you have to consider. Okay. So when you have double charge or two charges, okay. So this is what actually is discussed in the next section, where we, we'll see that. See the potential energy in an external field. So the external field, we don't need to consider like what is the source of the external field and all. You don't have to consider all those things. You don't have to consider the effect of the external source on this charge itself. Or if you have a single charge, you don't have to or don't need to consider the effect of its own potential. Okay, when there is another charge, then you have to consider. So look here, it is written clearly. If you have uh, such a field, see the work is stored in the form of potential energy. So if the point P, where the charge is now, has the potential actually V, okay, so the potential energy in that region or at that place in this external field will be Q into V, or generally we write Q as, like, Q is the charge, like from the quantization, charge quantization, we know any charge we can express in multiple integral of electronic charge, which is actually fundamental charge, we say that is having amount 1.6 into magnitude, obviously I am taking 1.6 into 10 to the power minus 19 coulomb. So look, this is another unit of energy. So if my delta V, if this V is actually 1 volt, that means the average volt. If I have average voltage 1 volt in this particular region what I am talking about, then I can write the potential energy or the work done to accelerate that charge particle through, or for going through that region, how much work he has to do, it has to do 1 electron charge into the volt. So if you just want to get the unit in terms of joule, see 1 into electron volt, so 1 E, that is the 1.6 into 10 to the minus 19, and voltage is, I have taken 1 volt. So 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule. So this thing is again important to learn. Suppose, so I have told that E into V is the potential energy, right? Potential energy. So this is called electron volt. This is also an unit of a unit of energy. So energy, again we have learned energy can be expressed in terms of joule. So whether there is any relation between this or conversion relation between joule and electron volt. The answer is yes, there is. Suppose I have taken 1 electronic charge, okay, that is actually 1.6 into 10 to the power minus 19 coulomb, okay, and if I take V as 1 volt, then I get 1 electron volt. 1 electron volt is equal to 1.6 into 10 to the power minus 19 coulomb into volt. Again 1 volt this is. So coulomb volt is actually joule, okay. So you get 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule. So this is the conversion formula, okay, conversion formula. When you need, see, suppose there is some unit, like there is a problem where you need to convert your electron volt to joule, suppose 5 electron volt to joule. So you have to just multiply with this factor, or either way, if you have some 5 electron volt, you have to get what is, sorry, 5 joule. So how much you have to get, like what is the value of this energy in electron volt? You have to just, what you have to do, you have to divide with this factor, okay. So this is the conversion factor, you should remember this during our atomic or molecular spectra, and also during our high energy physics like nuclear reactions and particle physics. That time we'll be using this conversion formula, okay. Oh, one more thing which it is not mentioned in your book, but this kind of problem is to come, and that will come in your modern physics chapter. So suppose this electron, this electron is moving in this region where I have average potential or potential difference between them. This is actually some voltage, okay, some maybe 10 kilovolt or something like that, okay, kilovolt, sorry, some 10 kilovolt, okay. So what is the kinetic energy of this particle? Can you tell? Can anyone tell me? If this is 10 okay, kilo electron volt, sorry, kilovolt potential in this region, okay, average potential, okay. So what is the, I'll ask, what is the kinetic energy or what is the velocity of the electron after coming out from this region? What will be the velocity of the electron? Suppose initially it was 0 velocity before it reached, so it starts from here, okay, with the 0 velocity, suppose, okay. So what will be the velocity after coming out from this region? See, you might have learned work energy theorem. Okay, what does that say? Work energy, that means, see, any equivalent work, like any work can be converted to equivalent kinetic energy, right? Any work can be converted to equivalent kinetic energy. So half m v square, okay, half m v square. So suppose my work done here is ev, or potential energy is electron volt, ev, okay. Then I can write ev or qv. I'll write qv. Suppose this is q. Q into v is equal to half m q mq, that means the charge of that particle v square. So from here we will be calculating the velocity of that particle. Okay, so 2 into qv divided by mq will be your velocity, and if you take the square root of this, so you'll get the velocity. Okay, and from here actually we'll be calculating, this is suffix actually. Okay, this is suffix. So from here we can calculate the momentum. Okay, momentum P is equal to m into v. So you'll see the momentum will be 2 q m q v, m suppose q into v. So this will be the momentum for the particle. Okay, this will come. This again will come. It will come. That's why I'm just mentioning over here. So in the modern physics, okay, de Broglie wavelength and all when we'll learn. Okay, we'll learn in the second part of your book. Okay, modern physics. Okay, so wave particle duality and all those things are there. This is okay. So this will talk about when the situation comes. Okay, so now here in the book you look. So that was for a single charge q into v. For a double charge, it will be like, say, when a single charge, that is only q into v, but see there are two potential energies. Okay, so now when I have two charges, for one charge, for a single charge, I know q2 into v. Okay, at certain point r2 inside the region, but this also will create a potential, right? So now for the first charge, I have to do work due to this. Okay, work due to this. Okay, and due to the potential created by the first charge. Okay, so I had already told you. I'll just briefly I'll repeat this, and then I'll move on to the next part. So what I'm talking, so suppose I have a potential, suppose average potential V over here in this region. Now you have two charges Q1 and Q2. So now what will be the potential energy, okay, for this system? Okay, so when they pass through, okay, or at any point, what will be the potential energy? Suppose at R2 point, this Q2 is there at R2 from any arbitrary origin, and this is at R1. Okay, R1 from any arbitrary origin, Q1 is here. At this situation, what will be the potential energy for this system? So see, I just take one by one. I'll take the Q1 first. So single charge, the potential will be like this at R distance. Okay. Now, if I bring, suppose, just imagine the charge is situated here. The Q1 charge is situated here. Exactly that time, the Q2 also enters in this region. So this potential is created by external source. But so this Q1 also will be creating a potential at this region, right? So that will be actually Q1 by 4 pi epsilon naught R12, suppose. Okay, at this place. So if this charge Q2 has to work for two potential, actually against two fields. One is actually this one, and another one is actually the potential, this V, which is already created by the external source. Okay, so now what will be the total potential energy then? So the total potential energy will be actually a Q1 into V, okay, then Q2 into V of R plus Q1 Q2 divided by 4 pi epsilon naught, okay, and R1 R2, the distance between these two charges, okay, Q1 and Q2. Okay, this is the potential, total potential energy when you have more than one charge. Okay, I mean to say two charges. Okay, this is the potential energy. So you can understand. So when I was bringing only one single charge, that time actually you have to consider only the external potential. But when I am bringing simultaneously two charges, you have to consider the presence of the other charge also, or the potential created by the other charge. Okay, this is what I have done here. Okay, so yeah, so this is the thing. So you will look here, there are certain numerical problems. I will just leave on you for the time being, because we have to like, our aim is actually first to cover the syllabus by teaching you the theory part. Then we will come back to uh, revision part. At least I thought of actually revising the chapters after finishing at least 2 chapters. Okay, so after second chapter we'll just do uh, some 2 classes for revision. Okay, for the first chapter and second chapter. That time we'll discuss the numerical problems and many other conceptual problems depending on the previous year's question paper. Okay, so now we'll be learning another interesting thing, that is this you have already. Oh, I'm sorry, just a minute. So suppose you have uh, you have an electric dipole which is kept at like kept inside an uniform electric field. Okay, in uniform electric field, then what is the potential energy of the dipole? So that is our question now, or topic of discussion now. See, look here. I have uniform field over here. I hope you are able to see my screen. So this is uniform. See, whenever I talk about uniform electric field, I can represent uniform electric field by equidistant parallel lines, which you might be seeing over here. Okay. Oh. Okay. So see, in this case, when you keep an electric dipole inside a field, see uniform electric field, this just 1 minute, it is actually the Microsoft. Okay, I'll go to the book again. Yeah. So look here, I have 2 charges. Like what do you mean by dipole? When you have 2 equal and opposite charges separated by a certain distance. Here 2a, see 2a is the distance. Okay, 2a is the distance of separation between two charges, plus q and minus q. So this is an electric dipole. And if you keep inside an electric field, see electric field exerts a force on the positive charge as well as on the negative charge. So in that case, I'll just open one uh, presentation so that I can express it in writing. It will just take 1 minute. Just can yeah, please wait for it. You please excuse me. I am actually trying to open one presentation so that I can write and tell you. Just wait for a minute. Yeah, I'm here. Okay. So we have so far learned that electric field exert a force on charges, right? So electric field will exert a force, like different type of force for different type of charges. That means if you have negative charge, it will attract, and if you have positive charge, it will repel. That we have learned. Okay. So if I have positive charge over here, negative charge over here, as you see in your book, so electric field is like this. Okay, uniform electric field, equidistant parallel lines are actually denoting your uniform electric field. And suppose the angle between this is actually theta, angle between electric field, direction of electric field. And see dipole, when I have dipole, we define a quantity called dipole moment. Okay, dipole moment, that is denoted by p, small p or capital P, you write. That is a vector quantity that we write as 2a q if you write the magnitude. A is the dimension, 2a is the dimension of the dipole, and q is the magnitude of one of the charge. And see the direction of this actually in this direction, okay, minus to negative to positive, okay, negative to positive, this way. So you have now dipole direction like this, okay, this is p, and you have direction of electric field this, and you have an angle theta over here. So when you have two charges, two different kind of charges, look for electric field. See, for positive charge, the force experienced by positive charge due to this electric field will be in this direction. Okay, and the negative charge will experience a force in this direction. Okay, and see, eventually these two forces will be equal, and they are actually not acting through a same. They are actually parallel forces. Okay, parallel forces. They are actually equal in magnitude, but their line of action is not the same. See, line of action for this force will be this way, and this will be this way. So line of action is not the same. So in this case, we can actually define a term called torque, okay, denoted by tau. So this is torque denoted by tau. So the torque actually is a vector quantity. So how do you define a torque? Torque actually is the magnitude, like force, any of the force. Suppose I take the F, suppose this is F minus, this is F plus. I take the F plus, okay, F plus cross the perpendicular distance, okay. If this is the this is actually perpendicular distance between these two line of forces. See, these are line of forces. This is this way, this is this way. So this is the perpendicular distance. So if this is actually 2a, length is 2a, then I can find out what is this distance, okay. If suppose we say this is x, so this is theta, means this also will be theta. So I can write, see, I have now, this is 2a, this is theta, and this is x. So what I can write is actually, suppose this is perpendicular, this is a, from the like trigonometric consideration, you can write x by 2a, that is perpendicular by hypotenuse, is equal to sine of theta, right? So you can get this perpendicular distance as 2a sine theta, right? So if you just, okay, force into the perpendicular distance, that is 2a. Suppose the magnitude of the force I am just calculating, 2a sine theta, and you look, this F is actually q into E. This is the force. Now you have q into a, 2a sine theta. I'll take some 5 minutes more maybe. Okay, 5-10 minutes more. Okay, so 2aq, this is actually p, right? I can write this as p. 2aq I'll write as p, then e, and then sine theta. Okay, this is p e sine theta. So in terms of vector, I can write this tau as p cross e. This I think you have learned even in the previous chapter also. So this is the torque. Now what is the role of torque? Still, force can have linear motion, can create a linear motion. Okay, force can create a linear motion, but torque can actually, see, in any rotational motion or circular motion, the torque acts actually. Torque has a tendency to rotate any object. Suppose this is minus q, this is plus q, this is a dipole. So it has a tendency to rotate the dipole. Okay, but since these two are actually equal in magnitude, so by itself it will not be able to rotate it. It will be forever like that. But if you somehow, if you actually just rotate it a little bit this way, suppose by angle delta theta, okay, delta theta. So if you just rotate this dipole by delta theta, then what will this torque do? This torque will try to rotate it back to its original position where the angle was actually between them theta. Okay. So suppose, So how much work done? So in this case, you have to find out the potential due to this potential of this dipole, potential energy of the dipole. So how do we calculate potential energy? The work done we have to calculate. How do we calculate the work done here? Suppose I have rotated the dipole, okay, by delta theta. So I have to do certain work by external torque, and that external torque is exactly equal to the torque here. Okay, that external torque dot delta theta. Okay, this is the angular displacement. Here actually we will be talking about angular displacement. Okay, angular displacement, suppose the object was here, if it goes up to here, this is theta or delta theta, whatever you take, d theta, this is the angular displacement. Okay, angular displacement. So I have made angular displacement delta theta or d theta. So I have to work against the torque here. Okay, or in other words, I have to say I have to apply another torque which is exactly equal to the torque over here. Okay, so which we know as P E sin theta. P is sin theta. I have to work against this torque. Okay, so I'll write P is sin theta and d theta. Suppose I am just taking, suppose at any point, this dipole was at certain distance, a certain angle theta 1, and bringing to theta 2 angle. So what will be the work done in this case? So I have to integrate it. I have to integrate, right? I have to integrate this. I'll just do that. You just look here. When I rotate the dipole from one position to another position like within the uniform electric field, suppose from theta 1 to theta 2, I have rotated. Okay, then what will be the work done? So the work done, I will calculate the total work done. I will calculate by integrating this. Okay, integrating this from theta 1 to theta 2. So what is this value? This we have got over here. Okay, this is dw p sin theta d theta. So I have to integrate it theta 1 to theta 2 p e sin theta and delta theta. So p is constant. Okay, electric field is uniform, so it will not change with the angle. Okay, so I'll just bring them outside the integration sign. Now I have to integrate for theta alone, d theta. Okay, so what will be the answer? So the answer will be, look, this is the total work done, PE. So sin theta, if you do integration, so you'll get minus cos theta, so minus sign over here, and cos, this is upper limit, so cos theta 2 minus cos theta 1. So this is the work done you have to do. Okay, this is the work done, and this will store as potential energy. So what will be the potential energy? This actually, yeah, this is the actually potential energy. Okay, for a dipole in an uniform electric field, if you rotate it from one angle to another angle, so this is the potential energy you will have. Okay, so suppose, see, I told you that at any case you have to find out a reference point for a potential where the potential energy is 0. So in this case, suppose my reference point theta 2 is actually 0, theta 2 is 90 degree, then my cos theta 2 will be 0. Okay, and theta 1 I take as, oh, I'm sorry, this will be theta 2, this will be theta 2 minus theta 1, I'm sorry, theta 2 minus theta 1. So let us take theta 1 as 90 degree as the reference frame where the potential is 0, because cos 90 will be 0, and theta 2 as theta. So I can write PE minus PE cos of theta. This is the expression for potential energy. Look, it is the same thing is done in your book. So this is the thing they have done. So theta 1, instead of theta 1 and theta 2, they have taken in this book theta 0 and theta 1. See here the external torque means you have to actually overcome the torque so that you can rotate it. That's why they have written external torque. So that external torque has to be exactly equal to the torque over here. That is P sin theta. That's why they have written P sin theta over here. And look, see the limit they have taken theta 0 to theta 1. So that's how they get this. And then they say the work stored as the potential energy of the system. We can then associate potential energy U theta with an inclination theta of the dipole. Similar to the potential energies, there is a freedom to choose the angle where the potential energy U is to be taken 0. Okay. So the natural choice is actually theta 0 is equal to 90 degree. So 90 degree, that means yeah, so this theta 0, this will be actually your if this is 90 degree, this will be 0, so you will get eventually you'll get minus p is cos theta, or I can write in terms of vector, I can write this like dot product will be anyway scalar quantity, so I can write p vector dot e vector. P is the dipole moment. Okay, P is the dipole moment. Okay, so this is how it is. So you just read up to this portion, and in the next class we'll just see the next portion again. Okay, so far do you have any like issue with understanding or something? You can tell me. Another 2-3 minutes maybe, then we'll stop the class. This is Kirtana, do you understand whatever I talk today? Whatever
Yes, sir.
I'm talking to this new girl, Kirtana.
Hello,
Have you
sir.
understood everything what I have taught? Yeah. Have you understood everything whatever I have taught today?
Yes, sir. Yes.
If you have any doubt, you can ask me.
No, sir. No. I haven't. Yes, sir. I understood your class.
Okay, thank you very much. And what about Nikhil? Do you understand everything here? Whatever we have learned today? Priyadarshini, I hope you also have understood everything. Or you
Yes,
have some
sir.
doubt, Priyadarshini. Okay, next day I'll take up some numerical problems. Okay, fine. Next day I'll take up some numerical problems, and then I'll just teach you the next portion of the theory. Okay? I'll take up few numerical examples or numerical problems. Okay? And then we'll continue with the next theory part. Okay? Okay, then we'll meet again on Sunday. Is that okay? Then we'll stop the class now here.
Yes, sir.
Okay. Bye. See you on Sunday.